Hi, my name's Bill, and I'm lumber rich and component rich and cash poor because I teach ours STEM classes. I'm an associate professor of engineering technology and the lead faculty for the guitar building. I drank the Kool-Aid back in 2010, and here we go. So I'm old school. I'm old. I'm wearing a tie here so that when my administrators see me, they won't recognize me. This is, okay. So I teach CAD, CNC, and the design prototype build class, which is more of a engineering documentation configuration management thing about how do you track and control changes over time, which is something we never really get to do in there. But guitars are perfect for that because students are willing to just work and work and work on it and get it right. So we use, we'll do all of our stuff pretty much in 2D. We use polylines, arcs and lines and points only so that you have legacy, to teach them how to do that. Whatever your G-code move, which is a straight line, clockwise, counterclockwise, that's it. No splines, no nerves, no ellipses. We create centerline toolpaths using the offset command, and then we tie all those centerline toolpaths together into one long continuous polyline as 2D, and then let our CAM software work our way down. So consequently, this is, and we're doing OGs, real smooth like baby's butt. That's how, I try to get them to go. The machine can quickly generate toolpaths from edges, but humans can be flexible and creative when creating those toolpaths. And this really gets to that point of when you're in a production environment and the machine is doing one thing, and you're busy doing that, but it's not quite optimized, or when somebody says, Bob, I need 2 minutes. I need 2 seconds off this part. We're not making money. And we're running it flat out. What can you do? So, and then this is my philosophy, which is a horrible admission, but it's true. CNC programming is typically not so much getting it right, but finding all must-fix mistakes and then making appropriate compromises until you get a finished part. So, with that being said, I also am a self-taught programmer, and I use that term very, very loosely, like I use the term instructor. I found out about Charles Simeone's Hungarian notation. He's the guy that worked with Bill Gates. He has enough money that he was, I think, either the second or the third civilian up at the Mir spacecraft. So he bought his way into outer space. He's that rich. But what he did for C language programming, primarily for Windows, you have multiple data types. Some are integers. You have double floats, arrays of pointers of type character. All of those Microsoft project stuff. So he came up with a way of naming variables by using a prefix in front of that to indicate the data type in the intended use. You embed information, and that prevents data mismatch. So you don't try to have an array of pointers of type character to equal to a counter, which is an integer. And that helps in troubleshooting, and it really helps in finding the notorious null pointer in C.
Also, architectural CAD layer naming standards. There are numerous ones of these. These are primarily for the folks that are in the architectural side. And we have an ISO standard, U.S. National CAD standard, American Institutes of Architects CAD, GSA public building stuff. Pretty much these were developed by the construction industry, but it really gets down to right here. Because these are for architectural stuff, it actually has to do with who owns that data, so who's responsible for it when things break and they can try to sue somebody. So that's kind of why the architects and the construction engineering people do that. There's no equivalent naming layer standard for mechanical or manufacturing industries that I could find. And I researched this. I did 3 or 4 wiki Google searches and found nothing. So that's my extent of searching. And part of that is just because of how you work. CAD, CAM, CNC projects are wildly variable. There's a lot of legacy data out there where people have been doing stuff. They keep doing it. They're all proprietary, or you're sharing projects between certain companies. You have a wide range of products, processes, and methodologies, and then equipment, and you have custom workflows. And there's myriad CAD and CNC platforms. So it's not really conducive to doing that. I'm sorry, am I walking out of frame? Guitars are a complex project, and you need some management tools. So the guitar is a complex data set. We want to have data reuse and sharing. We want to take neck pocket and humbucker pocket and all those constant things, and then, you know, bring them in and just import them. So they're concentrating on working on the outside or F-holes or whatever they're doing for their custom work. And we also do team building things, because right after the guitar class, which is an individual class, we go into a capstone program, a senior level program, where we get our college is business and technology. So we have business students working with engineering technology students, coming up with ideas and then building products, voting on those prototypes, and then going in and doing limited production, all in 15 weeks, which is a real riot. Few fist fights, but lots of arguing. Goals: embedding the information and help organizing the data. That's really what we're trying to do here. We want to speed development, so this plays into that concurrent engineering or simultaneous engineering. We want to reduce our programming errors and aid in fixing the errors that we have. So, over the years, we've just started doing stuff, and finally I got so tired of explaining it, I decided to write it down and then make it into a document that nobody would understand. And, whoops, sorry. This is the lie right here. I made the mistake. So, if you're an MBA, it's always continuous improvement. If you're an engineer, better is the enemy of good enough. Good enough is the 4-page document that lays out the best practices and 2 pages of this name layer standard. Right now it's up to 6 and I haven't finished yet, but we still have one out there for you to use. It's a collection of CAD standards that we use, best practices, and this layer naming convention that I'll talk about for the rest of the thing, and it's incredibly helpful. Here's what it is. This is why I said it makes no sense. So I'll explain to you how it is, and then we'll just talk about what you're going to see, show you how it works. Our type ID is for, like, what is it? Is it a toolpath? Is it an edge? Is it a reference? Is it a point? What is it? And so we have a whole series of them. And this is typically just 2 letters. Then we have the orientation, bottom, top, left, right, whatever we need. After that, if you want to, you can bury some kind of design information in there, specifically diameter. And then we have a dash, and then the descriptor, a major descriptor, oh my goodness, that should have been an underline, and then a minor descriptor. And you'll see that I have like capital letters and lower letters. Those are all kind of important. Here's how you read it. It's very, very simple. Center path bottom. It's a 1/2 inch diameter. It's for the deep cavity or the E-pocket. If we have this is a center path top, 0.188, which is a 3/16 diameter, and this is for the tone or volume pot hole in the top. So you kind of read things backwards. It's like a bill of materials in that regard. And so, you know, this is like this is an edge on the bottom of that deep cavity. We have EL, humbucker, generic. So if we just have a picture of a component, that's just going to be an EL. And a reference is something like the 21st fret of a 500 spring length, which is 25.5. And so about the numbers that you'll see, our machines are, we have a large gantry style CNC, but the biggest cutter we can use is basically 2 inches. So what we said was that our first digit here is going to be our integer. So if it's less than an inch, it's a 0. And then we have thousandths of an inch. So that's why a 1/2 inch would be a 0.500, 1/4 inch 0.250, 1/8 is 0.125, and our largest cutter is a 1500 core box. which we call the beast. 5 minutes. Okay, here we go. Here's how it all looks. So this is the Lucy right here. It's standard thing. This is every layer turned on. Because I knew it was getting kind of weird. I have 82 layers that describe that guitar. It's edges, top and bottom, all sorts of stuff. Our centerline tool pass for the bottom, there are 10 of those, 10 for the top. Laser edge parts, we have 6, which is basically broken into 2 things. We have 22 edges, and electronics and hardware, 8 of those, dimensions of 0.6, and then notes and reference data. So this is, I don't want you to try to read this. I want you to understand what we're doing. We're also using color coding. So if this right here, blue means top, green means bottom, and then we have our points and reference data in different colors. So I can look at something, and if it's the wrong color, and this even works with colorblind students, they just don't have the variation that you could do. But you can see right here, I have green here for the bottom, blue for the top. There's my gray for the electronics, orange for points and things like that. The neat thing about this self-organizes. And so what we have here is when I'm looking at my bottom, by having that CPD, they're all here. I don't forget to pick something up. So when I'm grabbing that data to put it into CAM, there it is. And then when it shows up, I just have that data when I copy base and then drop it into the new drawing. Same thing with the top. I grab them all at the same time, unselect the one I don't want, and then drop that into my CAD DXF for my output. We also use spreadsheets, and we actually use them to calculate, so I can put in my depth here, and it starts calculating what my depths are going to be to maintain relationships. But here's what's really cool. There's my named layer. That goes here, and then we're going to check. So if I'm going to be using the tool, there's my 3/8, there's my assorted 3/8 right there. And so now I can check and start preventing errors. We change those to the colors. So this is what's going to the machine. And then here's our laser work. Same thing here. One of the cool things that we do is we throw our electronics schematic onto the back of the cover. Yeah, it's really slick. It looks like it's, worth a lot. We also, if we're going to have a cavity pocket here, we'll laser around that and then spray tape it, pull the tape off here, spray paint that black, and we get really black thing. So when we'll copy it there, pull it over here, but we'll just use 3 layers. Our raster etch is black, vector cuts are red, vector etch is blue, and we just use those. So in summary, appropriately named layers greatly help in understanding complex data sets and relationships. They're self-organizing. You don't forget to bring things over. They enhance communication between team members and faculty trying to understand what the hell are you doing. And then we prevent errors in speed troubleshooting and speed development and increase quality of the final part. If you want to get it, and y'all have this, that's available now. It's not a great document, but it's a document. If you want to get it, the easiest way to do it, Google my name, ETSU portal, and then find that link. The other thing you can do, we have over 1,200 pictures of various builds on our Facebook page, documenting what our students do, and we're posting stuff. So anytime this is updated, we're there, and there's my contact information. So if you ever want to find that out, if you have any suggestions for things to add to it, it's not an open source document. It's like the first source document, and we don't know what the hell we're doing. But if you find it useful and you want to implement it, or something like that, we've done it informally because we just kind of created this thing to keep from making mistakes. But it's turned out to be things like our advisory board members during a meeting, when we showed this to them, one of my former students goes, "I need this right now on my shop floor. Can I use it?" I'm like, "An educator, of course you can." you know. And so, if you want to try it out, please do. It's really kind of cool how things will self-organize though, if you just spend a little bit of time naming it. So, thank you.